Right, are we everyone here? Yeah, we're not expecting anyone else, so fine, good. Okay, right. Well, I mean, actually, I don't need it, do I? After all that. I'm used to shouting, I'm used to lecturing loudly in large lecture theatres, so people can't hear me at the back. It's your hearing, not my voice. Decide. Okay, so, also, is it possible to turn the lights down at all, or just so it's a contrast for the... Brilliant, yeah. Oh yeah, that's better. Good. So, first of all, I should blame Joe Ward here for his persistence in making sure that I did come along to give this talk. I can't remember now whether, did I say no first time or?
Yes.
I did, okay. Good. I was just checking, I didn't want to sort of any favouritism.
I think you said come back next year and then he emailed you on New Year's.
Yeah, that's exactly it. Yeah, that's right. No, I'm too busy this year, but come back next year, and then usually that puts most people off. But the fact that you came back on January 1st, 5 past midnight or whatever it was, it is now 2014, you did say. So, it's not much I could say. I couldn't have filled in the 2014 diary 5 minutes after midnight. Okay, so this talk is based on a book I wrote a couple of years ago, The 9 Greatest Enigmas in Physics, or the 9 Great Enigmas in Science. It so happens that these paradoxes, these enigmas I'm going to be talking about, are mostly from physics. An explanation for those of you who might be curious about the image, that's on the front cover of the American edition of the book. And it's basically Schrodinger's cat inside an Escher cube. Now, Escher, the artist, is famous for these paradoxical images. The Escher staircase, where basically you climb upstairs, go all the way around, and you arrive back at where you started from. So the optical illusions. So there's this optical illusion cube. I'm mixing that paradoxical cube with one of the most famous paradoxes in physics, namely the paradox of Schrodinger's cat. I'm going to test you. I'm going to give you headaches. I'm going to be throwing brain teasers at you. But I wanted to start with letting you know what I mean by a paradox in science. And I'm going to show you a clip from a TV documentary I made 7 years ago now, called Atom, in which I explain the essence of the Schrodinger's cat paradox, what it's all about. Hopefully the technology all works.
It's called the Schrodinger's cat experiment. Erwin Schrödinger was one of the founding fathers of atomic theory, and in the mid-1930s devised a thought experiment purely to highlight the absurdity of quantum mechanics. He suggested you take a box in which you place an unopened container of cyanide connected to a radiation detector and some radioactive material. Now, the idea is that if an atom in the material emits a particle, this will be picked up by the detector, which in turn releases the cyanide. Next, you take Schrödinger's cat, which in this case is a lovely Norwegian forest cat called darken. Now, I should point out that this isn't real cyanide. You place the cat in the box, you close the lid, so here's the conundrum. According to traditional quantum mechanics, known as the Copenhagen interpretation, all the time the box is closed, the radioactive atom inside has yet to make up its mind whether it's decayed and spat out a particle. So we have to describe it as both having decayed and not decayed at the same time. Think about what this means. Since the radioactive particle triggers the release of the poison, the cat is both poisoned and not poisoned. So until we open the lid to check up on the fate of the cat, what's called making a measurement, it's not just that we don't know, but that the cat is literally both dead and alive at the same time. This is clearly a paradox, or is it?
We've got one complaint from a cat lover after that programme was aired on BBC. How could you put a cat in a box for an hour like that with all the poison? First of all, there wasn't any poison, it was pretend. Secondly, this is TV. You put the cat in the box, you close the lid, you cut, you open the lid, take the cat out, give it back to its owner, and then you carry on. Didn't really have to leave it there for an hour. Erwin Schrödinger was one of the founders of quantum mechanics, and in the 1930s, even quantum mechanics is so weird as a theory that describes the subatomic world that even one of the people who first comes up with a theory is unsure about how it could be right. And he came up with this paradoxical situation. How can a cat be dead and alive at the same time? It's nonsense. Surely when the box is closed, you simply don't know whether it's dead or alive at the same time. It's not that it really is, because when you open the box, you never catch it in that in-between state. So this became one of the most famous paradoxes in physics, and most people who have some interest in science will have heard of the paradox of Schrödinger's cat, even if they haven't studied quantum mechanics or haven't understood the details of what it means. But what I want to talk about are paradoxes like this, which have been called, they've been labelled a paradox, but they're not real paradoxes. They've been resolved, they've been explained, they're only perceived paradoxes. You see, the thing is, nature should not be paradoxical. If there's some aspect of nature, something we haven't understood, that suggests a paradox, that's our shortcomings. That's because we haven't quite figured out the details. Hopefully when we learn more, understand more about that phenomenon, then we realise it's not paradoxical at all. Schrödinger's cat also fits in that category. In fact, we know now, and in fact for some of the upper six, I was chatting to them before the lecture, we're talking about issues like this. Once a quantum system, by which I mean something very small, an atom or an electron, a particle that makes up the atom, once it becomes embedded within a more complicated environment, such as the trillions and trillions of atoms that are needed to make up a cat, then all the quantum weirdness disappears very, very quickly. Cats are never dead and alive at the same time. The atom could be doing weird things, but once you zoom out, all that weirdness dissipates very quickly. So it's as though the cat, when we say we open the box and look, we force the cat or everything inside to make up its mind, the cat is also doing the looking. The cat is forcing that atom to make up its mind. Because otherwise you can say, well, hang on, what's so special about us looking inside the box? Do you have to have a PhD to make a quantum observation? Do you have to wear a white lab coat to do it? Why couldn't the cat? What about if you put Schrödinger in the box and see how he likes it? Is he going to be dead and alive at the same time? So this quantum weirdness really does seem to be constrained in the quantum world. And one of the challenges in physics today, for instance, in trying to develop something called a quantum computer, is to stop all that quantum weirdness from disappearing very, very quickly. We want to make use of it because it turns out to be very beneficial, for instance, in designing a certain type of computer. So Schrödinger's cat paradox is no longer a paradox. It's only a perceived paradox, but a useful tool in explaining something like quantum mechanics. Here is a real paradox. This statement is a lie. Think about what it means. If it's a lie, then it's lying about the fact that it's a lie. Therefore, it must be the truth. Therefore, it really is a lie. Therefore, it's not a lie. And so on. You go round and round and round in circles. It can drive, well, basically it's rather boring because it doesn't take you anywhere. It is a true paradox of logic because it goes round in a never-ending circle. It doesn't teach us anything. Those are not the sorts of paradoxes that I'm interested in. I'm interested in riddles that have, if someone comes up with a really good puzzle or riddle for you, they say, oh, okay, I give up. What's the answer? There isn't one. Oh, thanks very much. It's frustrating. So these perceived paradoxes are much more interesting, and there are two types. There's something called a veridical paradox. Into the detail and think about it more carefully, you realise it's not. Most of the paradoxes I'm going to talk about in this lecture are of this type. There's another form called a falsidical paradox, which it's also not a paradox, but not because you haven't thought about it carefully enough, but it's the way it's told. There's a flaw in the logic that usually is used to trick you. Now I'm going to give you an example of both of these. And I'll give you several examples throughout this talk. Many of them, I suspect, some of you will have heard before. Example of veridical paradox was told to me by another professor of physics working in my department. He's a Scottish professor from Edinburgh. It makes a lot more sense if you're Scottish, this paradox. He said, every Scotsman who travels south of the border to England raises the average IQ of both nations. Which sounds paradoxical. But then if you think about it carefully, and the way a Scotsman will think about it, an Englishman might not agree, and it says, since all Scots are more intelligent than all English, any Scotsman who travels south of the border will be cleverer than everyone in England, so he raises the average IQ of England. But he would have to have been a pretty stupid Scotsman to want to leave Scotland in the first place, therefore leaving behind a more intelligent Scotland. So logically, it makes sense. That's a veridical paradox. Once it's explained, you think, oh yeah, of course. A falsidical paradox, on the other hand, okay, well, I'll hit you with this one. It's the paradox of the missing dollar. Now, I don't know how many of you have read my book or indeed have come across that. Show of hands, who's heard of the paradox of the missing dollar? You might recognize, yeah, so a few of you might recognize it in the telling. Anyway, it goes like this. 3 friends check into a hotel and to share a room for the night, and it costs $30. So they each pay $10. They get the key, they go out to the room. In the meantime, the guy behind the desk realizes they had a special offer on that week, and he should have only charged them $25. How many more people now realize they've heard this one? A few more. Okay. Those of you who've heard it, don't tell the answer. I'm going to throw this to the audience, think about it, and remind me at the end, and I'll give you the solution. And I guarantee you don't feel ashamed if you can't get the answer. Right, so the receptionist realizes he's overcharged them. He takes $5 bills from the till to go up to the room to pay them back. On his way there, he realizes he can't split $5 3 ways without breaking into change. So he thinks, I know what, the easiest thing is if I give them back $1 each and I pocket the other $2, everyone's a winner. And that's what he does. He knocks on the door, sorry chaps, overcharged you, gives them $1 back each. Here's the paradox, the perceived paradox. They've now each paid $9. 3 9s are 27, plus the 2 in his pocket makes 29. Where's that last dollar gone? Yes. Scary, isn't it? Scary that something as simple as that. And trust me, I've tried this on fellow physics professors, and they all go away, they get very, very disturbed by this. Okay? So I'll leave you to sort of dwell on that a bit. Not too much, because I need you to listen to me as well. But we'll revisit this at the end. Okay. I want to cover, I want to leave enough time for questions, so I won't get enough time to go through all of these paradoxes, but the paradoxes that I cover in the book, I will talk about the Monty Hall paradox, the game show paradox. I'm sure a number of you will have heard that one before as well, but that's such great fun. The paradox of Zeno, Olbers' paradox, I'll cover those. I won't go into Maxwell's demon or Laplace's demon, the twins' paradox of relativity or the Paul and the Bun. I might talk about the grandfather paradox of time travel if I have time. Schrödinger's cat paradox I've covered. Fermi's paradox, we'll see. Anyway, there are lots of these paradoxes. Some of these names you may have heard of. Many of them you'll not be familiar with. But they are all puzzles, mostly in physics, that have occupied some of the greatest minds, often over the course of centuries. I want to start with the Monty Hall paradox. So it's named after this guy here, Monty Hall. He's a Canadian-born American game show host. And he used to present a game show called Let's Make a Deal, on which the even more stupid Deal or No Deal I don't know whether Let's Make a Deal involved people all holding hands saying, yes, my grandmother told me to open box number 23, or some other such nonsense. But, you know, Let's Make a Deal was also quite simple. Before I explain the paradox, I'll say something about the history of how it developed. It was first devised by a mathematician, a guy called Steve Selvin, American mathematician, worked in Berkeley in California, and he devised this little maths puzzle and published it in a journal of statistics. And a lot of other mathematicians who read this very learned journal, oh, that's very interesting, you know. But it didn't really sort of seep out into the wider world. It only made the headlines among the public when it's published in this magazine, Parade magazine. It's a weekly magazine in America, huge circulation, millions of copies. And in Parade magazine is a woman who writes a column, Marilyn Vos Savant. She's basically like an agony aunt come problem solver, so people would write in either with sort of relationship issues or things like mathematical puzzles. Why would she be able to answer them? Well, Marilyn Vos Savant had, during the 1980s, the honour of being in the Guinness Book of Records for having the world's highest IQ. Depending on how you measure IQ and intelligence, 190, 200, some astronomically ridiculous number. Of course, we realise now that IQ tests are not very good indicators of how intelligent someone is. Nevertheless, this is a smart woman. Why she chose to write this column for Parade magazine rather than going off winning Nobel Prizes is her business. A reader in the early 90s, okay, so about 20 years ago or so, a bit over, wrote in with the Monty Hall, the game show paradox, to her. And in the next edition, she published the solution. The answer she gave was the correct one. But she kicked up a storm of controversy. People were writing into the magazine, complaining that she got it wrong. And I'll give you an example of a few of the things that people wrote in. As a professional mathematician, I'm very concerned with the general public's lack of mathematical skills. Please help by confessing your error, and in the future being more careful. So, you know, that's told her. You blew it, and you blew it big. You seem to have difficulty grasping the basic principle at work here. There's enough mathematical literacy in this country, and we don't need the world's highest IQ propagating more. Shame. Yeah, these people are not pulling their punches. It gets better. May I suggest that you obtain and refer to a standard textbook on probability before you try to answer a question of this type again? I am in shock that after being corrected by at least 3 mathematicians, you still do not see your mistake. And my favourite one of all, maybe women look at math problems differently. I mean, these are people, and people with PhDs were writing and complaining. They were all wrong. They all ended up with egg on their faces because Marilyn Vos Savant was right. It just goes to show that here's a simple puzzle in probability that is so counterintuitive. So let me explain what it's all about. It's very simple. The game show in the title is because, you know, the basic principle is that Monty Hall, the game show host, offers you, the contestant, the choice of one of 3 doors. There's a prize behind one of those 3 doors, and you have to choose which one it is. How many of you have come across this before? So about 1/3 of you. Okay, good. That's fine, for the benefit of the other 2/3. Let's say you as the audience, you choose door A. You have a 1 in 3 chance, a 1 in 3 chance of being right. Okay, you don't know where the prize is. Now, the way it was first devised by that mathematician, Steve Selvin, which was back in the mid-1970s, his prize was a car, and then behind the other 2 doors were goats. Sure why. The assumption being that, you know, you're not a goat-loving cyclist, and that you would really like to win the car. Anyway, there's a 1 in 3 chance that the door you pick has a car behind it. Let's say you pick door A. As the game show host, I'm going to help you out. And I'm going to open door B to reveal a goat. Now, the prizes now must be obviously behind, there is the prize there, it's got to be behind A or C. You've chosen door A. I offer you now the chance to change your mind. Of those of you who don't know the game show host, the game show paradox, how many of you would stick with door A? Hands up. And how many of you would switch to door C? Okay, about the same, but many more really don't know what to do. Pressure. And I've given this talk to huge audiences. I gave this talk as a lecture in India a few months ago. And there were like 1,000 people in the audience. And statistically, when you get that sort of number, it's quite nice that 50% said yes, we would stick with A, and 50% said no, we will switch to C. Those who stick to A say, okay, now look, I chose A, and for whatever reason, I'm going to stick with it. You're not going to fool me. And those who switch to C thinking, I wonder, has he given me an advantage? Go on then, I'm going to take a chance and switch. But deep down you think, well, hey, it doesn't matter. It's 50-50 now, right? It's 50% chances behind A, 50% chances behind C. Wrong. The correct answer is that you should always switch to C. The chance of the car, it's a small car, if you fit through a door, is behind A, is still only 1 in 3. And the chance that it's behind C is 2 in 3. So you're twice as likely to win the car if you switch to C. How can that be possible? This is the paradox. How is it possible? It's random. You don't know where the car is. It could have been behind A, B, or C. B's been ruled out, because I know where it is and I've shown you it's a goat. So it's got to be A and C. How come they're not equal in probability? Well, I'll tell you, I'll explain the solution to this. I won't leave it till the end to let you stew on too many problems. Yes, it is correct that you're twice as likely to win if you choose C to A. There are various ways of explaining this. The nicest way that I'm aware of was actually told to me by the unlikeliest of sources, the comedian Dara Ó Briain. Now, Dara Ó Briain has a degree in physics, theoretical physics, and he's a smart bloke, and he likes this sort of thing. He likes these puzzles and paradoxes. And he didn't come up with this explanation himself. He'd heard it from somewhere else, but that's where I heard it from, so I should give him credit. He said, imagine if you didn't just have 3 doors, imagine you had 1,000 doors. You choose door number 1. You have a 1 in 1,000 chance that you're right. I, as the game show host, and here is the crucial thing, I know where the prize is. I then proceed to open door 2, there's a goat. Door 3, goat. Door 4, goat. All the way out to door 556, goat. I leave door 557 closed. 558, goat. 559, goat. All the way out to door 1000. I've opened all the doors showing goats. You're now left with door 1, which you first chose, and door 557. Are you going to stick or are you going to switch? Damn right you're going to switch. There's something special about door number 557. And sure enough, door 557, it's 999 out of 1,000. Almost definitely the car is behind there, not behind door 1. You see, the crucial thing I mentioned is that I know where the car is. Were it behind door number 556, I'd have left that one closed. Were it behind door 201, I'd have left that one closed. Wherever the car is, that's the one I don't open. I open all the redundant doors that we don't need, because I know where the car is. So all that probability, the 999 over 1,000 that's behind any of the doors other than the one you chose, all that probability gets lumped onto the one door that I've left closed, because all the others, I'm telling you, the car isn't behind them. And the same explanation applies when you drop down to 3 doors. The other way of explaining it is, you choose door A, 1 in 3 chance. There's a 2 in 3 chance it's behind door B or C. If it's behind C, I'd have opened door B, as I did. Were it behind B, I'd have opened door C. I always open the door that doesn't have the car. So there's twice the chance that you'll find the car because I will always open the other one. So the 1 in 3 and the 1 in 3. And if you don't believe me, you can do this trick yourself with friends. With 3 cards, you can have 2 red cards and a black card, the black card being the prize, and put them face down, and ask your friend to pick one. Or pick the black card, guess the black card. Then you can see where the red and black card is, and always turn up the other, of the other 2 cards that have not been chosen, turn over the red one and say, right, do you want to switch or stick? If you do this statistically enough times, I'm probably doing it 20 times is quite enough. You will see that when they switch, they're much more likely to get the prize than if they don't. Okay, so that's a lovely example of a veridical paradox. It's not a paradox of physics, it's a paradox of pure probability theory, but it's such fun that it gets you thinking about some of these ideas. Okay. The oldest paradoxes in science go back to a Greek philosopher by the name of Zeno. Now he devised lots of different paradoxes. They were all to do with the nature of time and space and motion. We don't know about them directly from him, but from later, more famous philosophers who wrote about it, like Aristotle and Plato. And there's a few that survive to this day. And I want to just talk about one of them, the paradox of Achilles and the tortoise. It's based on an even older story of the hare and the tortoise, a fable which goes back even older than Zeno, many thousands of years ago. But Zeno modifies the hare and the tortoise story. You know, the hare and the tortoise, they have a race, the hare gives the tortoise a head start, and the hare sort of follows after, then goes to sleep or goes down the pub or whatever he does. Zeno modified it. He says, no, instead of the hare, I'm going to take, as my champion, Achilles, the half-man, half-god warrior who's powerful and fast. And he says, right, this is the paradox. Achilles gives the tortoise in a race, he gives him a head start. After a certain time, Achilles then heads off. He's not stopping. He's not stopping for a rest. He's not going for a pint. No toilet breaks. He's just start to finish. The paradox is this. When Achilles starts off, let's say the tortoise has reached some point in the race. Let's call it A. By the time Achilles reaches A, the tortoise has reached point B. Not so far. A to B is not as far as the beginning to A because Achilles is running faster than the tortoise. By the time Achilles gets to B, however, tortoise has moved to C. By the time Achilles gets to C, the tortoise has moved to D, and so on and so on and so on. In an ever-decreasing infinite series, Achilles never overtakes the tortoise. Strange, isn't it? Seems logically foolproof, but Zeno has just come up with a scenario whereby it doesn't matter how fast Achilles is running, or how much or little or larger head start he gives the tortoise, he would never be able to overtake him, which clearly is paradoxical, because you'd think, given a long enough stretch, he should overtake him easily. Well, of course, Zeno didn't understand various concepts that we take for granted that we learn at school today. For instance, speed equals distance over time, or the notion of an infinite geometric series. Because yes, every one of those steps start at A to B, B to C are getting shorter and shorter and shorter. The relative speed between them, the speed at which Achilles is catching up with the tortoise, is constant. Now, constant speed, speed is distance over time. Constant speed means that if the distance is getting shorter in every step, the time interval between the successive steps is getting shorter. You can add an infinite number of ever-decreasing intervals. The answer isn't infinity. You can't say it will take an infinite amount of time for Achilles to reach the tortoise. No, it'll take a finite time. Add 1 plus a half, plus a quarter, plus an 8, plus a 16th, plus 1 over 32, plus 1 over 64. You could go on forever. So just because you're adding an infinite number of steps doesn't mean that the answer has to be infinity. So as Achilles runs to catch up with the tortoise, every one of those steps, A to B to C to D to E and so on, is taking a shorter and shorter time. Let's say an infinite number of ever-decreasing intervals of time that will add up to 10 seconds. By the 11th second, he's overtaken. So he does indeed overtake him. Zeno's whole philosophy was about the notion that motion was just an illusion. It didn't exist. There were a group of philosophers at the time that, this is the way they study. One of them would stand up in a square in Athens and pontificate about something philosophical. So Zeno would have been talking about, there is no such thing as motion, it's all an illusion. One of the philosophers sitting around listening to him had had enough. He stood up and said, motion is just an illusion, I disprove you thus, and walked off. Thus proving Zeno was wrong. Okay, so paradoxes go back all the way to the beginning of mankind's thinking about the nature of the universe. I want to tell you about my favourite paradox in physics, Olber's paradox. It can be stated very simply. Why does it get dark at night? Now you might think that's a trivial question, because the sun goes down. Because we don't have enough light, from the moon, or reflected light from the moon, or the light from the distant stars, as bright as the sun. But actually, it's a serious question. Imagine you were in a forest, an infinite forest with trees that go on forever, and you fire an arrow horizontally. Now we have to ignore gravity, so we have to assume that arrow will never get down to the ground. Just carry on going horizontally until it hits a tree trunk. You could try very hard to avoid all those tree trunks, that are close to you. Try and find the best gap so the arrow doesn't hit the tree trunk. If it's an infinite forest, sooner or later it'll hit a tree trunk. And it doesn't matter if you chop down 90% of the trees in the forest, all that happens then is that the arrow will on average travel 10 times further. Now, imagine the opposite, and you're looking up at the night sky. If the universe is infinite and goes on forever, there will be a star in every direction, every line of sight you care to look. It doesn't matter where you look, try and look gaps between the stars, you will always see a star in your line of sight. So why isn't the night sky full of stars? Why isn't it in every point in the night sky there's a star there? And if so, the night sky should be ablaze with light, as bright as the surface of the sun. Now, first of all, we know that stars are clumped together in galaxies, but that's fine, that doesn't affect the issue. I mean, we could imagine a galaxy in every line of sight, fine, but then it just means that there should, the night sky should be as bright as the surface of an average galaxy, still blindingly bright. This paradox goes back hundreds of years, and I will explain a little bit about the details in it as I go along. Now that doesn't show up very well, but that's meant to be a picture of Copernicus. Copernicus, the astronomer who really was one of the people who kick-started modern science. Until Copernicus, most astronomers believed that the Earth was at the centre of the universe, that the sun orbits around the Earth. After all, you look up at the sky, that's what you see. And without the benefit of a telescope, it's understandable why people would think that. There have been other astronomers going all the way back to the ancient Greeks and the ancient Babylonians who suggested that maybe the sun was at the centre and that the Earth was just orbiting the sun along with the other, they weren't known as planets, but the other heavenly bodies like Mercury and Mars and Venus. And they were right. They said, no, the only thing that orbits the Earth is the moon. The Earth itself goes on. They were right, but no one really believed them. And it took Copernicus to finally get a proper mathematical theory to explain his what's called the heliocentric model. Helio meaning sun, the sun at the centre, not the Earth, not the geocentric model of the universe. And of course, Copernicus was lucky because a few years later, Galileo turns up with a telescope, looks up at the sky, and sure enough, sees that the Earth is really going around the Sun. In fact, what he first notices is that Jupiter has moons that go round it. And until then, it was thought that everything goes around the Earth. Now, if things can go around other things, then suddenly the Earth isn't so special. So, Copernicus says the Sun's at the centre of the universe. Of course, what Copernicus also thought, which wasn't right, was that the Sun wasn't just the centre of our solar system as we know it today, but the centre of the entire cosmos, the entire universe. So even the stars go around the Sun. Olbers' paradox first came to prominence when an English astronomer by the name of Thomas Digges took Copernicus's idea a step further. He said, what if those stars are not orbiting the Sun? What if the Sun is just another star? And take all those stars and scatter them out into infinite space. Which is correct. Obviously, people didn't know about galaxies then, but that's or indeed the universe is expanding, that's a secondary detail. So Digges, in doing this, realised that this would cause a problem. Because if the universe went on forever, then we have this issue that the night sky should be ablaze with light, because there should be a star in every direction we can see. Well, many astronomers, Digges was in the 16th century. Then the next century, Kepler, the astronomer who famously explained that the planets go around the Sun not in circles, but in ellipses. Kepler also thought about this paradox of why the night sky was dark. His idea was that the universe didn't go on forever. It was finite in size. So basically, when you look out there, what you see is what you get. That's all there is, which seems a reasonable assumption. A century after him, another English astronomer, Edmund Halley, in the early 18th century, said no, the universe could be infinite in extent. However, a much more sensible explanation is that the further away you look, the dimmer the stars are. That seems so logical, doesn't it? Well, you don't see the really distant stars because they're too dim, because they're too far away. But when astronomers did the calculations, the maths, they found there was a problem with that explanation. If you were to hold up a coin, a 10p piece, arm's length, that sort of blocks off a patch of sky, then let's imagine the sky out into deep space it's built up into concentric shells, that you're at the centre and you've got these shells that are ever larger radius away from you. Stars sitting on an inner shell, that 10p piece will block off, say, 2 or 3 stars. They're close, they're bright, they have some combined brightness that's being blocked off. That same 10p piece would block off a larger area of a more distant shell. Now, if stars are equally separated from each other, let's say they're distributed evenly throughout the universe, we know they're not, but let's say they are for simplicity, then many more stars will be blocked off by that 10p coin if they're sitting in a distant shell. If you do the maths, you realise that the total light coming from the fewer, brighter, nearer stars exactly matches the total amount of light coming from the more distant, dimmer, yet more plentiful stars in the outer shell. So it doesn't matter. The idea that more distant stars are dimmer, therefore they don't contribute, doesn't help us because there's more of them, cumulatively, to give the same brightness. The paradox was named actually after a 19th century astronomer called Heinrich Olbers. It's only really named after him by accident because a guy about 50 years ago wrote a textbook and he wasn't aware of the history behind it, and so he thought Olbers was the first person to originate it, not realising it goes all the way back centuries. Olbers said, no, there's an even simpler explanation. Basically, most of what's out there isn't stars, but dust and gas. Clouds of hydrogen and helium and just dust. And that block off the light from the more distant stars. because the universe has been around long enough that dust and gas will absorb the light's radiation from the objects that it obscures and gradually heat up until eventually it will glow and shine with the same brightness as the objects it's obscuring. So it doesn't help you. Now, of course, today we know that the universe is expanding. That was discovered in the 1920s by Hubble. That doesn't explain all those paradoxes. It helps, but it's not necessary. The person who really explained it wasn't an astronomer at all. It was the American writer and poet, Edgar Allan Poe. Now, Edgar Allan Poe died in his early 40s, and the last essay he wrote was called Eureka, and in it is this resolution of Olbers' paradox. Now, Edgar Allan Poe is one of those people who thinks, he comes up with his own theory, of the sort that I get lots of letters and emails from people. I'm told I can't call them nutters, but people who, have developed their own theory of particle physics over the course of many years, without the benefit of a physics background. But nevertheless, they think they've got it right. Edgar Allan Poe was keen on pontificating about aspects of the physical universe that he thought he'd figured out, and where Isaac Newton was wrong and how he corrected him. So most of it was nonsense, but in the middle was this nugget of truth, the resolution of Olbers' paradox, and it's this. The reason it gets dark at night, the reason why the night sky isn't ablaze with light, is very simple. The universe could be infinite, we don't know, but it's not infinite in age. The universe had a beginning, and so we only see the light from those stars and galaxies, it's galaxies once you get beyond the Milky Way, that are close enough to us for their light to have reached us since the beginning of the universe. So anything further away than 13.8, the expansion of the universe complicates matters. Let's pretend the universe isn't expanding, but was created 13.8 billion years ago. Anything further away than 13.8 billion light years, that's the distance light can travel in a year, well, for their light to reach us would take longer than the age of the universe. So their light hasn't reached us yet, it's still in transit. So we only see those objects close enough to us for their light to have had time to reach us. And that's why we don't see the entirety of the universe. So Olbers' paradox is resolved because the universe had a beginning. And I find this really lovely because you can turn it on its head. A lot of people will ask physicists and astronomers, how do you know there was a Big Bang? You weren't there. How can you tell? You can hit them with all this sort of very careful empirical evidence, like, the temperature of deep space is predicted by the Big Bang to be just under 3 degrees above absolute zero, and sure enough, you measure it, that's exactly what it is. We see through our telescopes the universe is expanding, it's getting bigger, so in the past it would have been smaller, and you can wind the clock all the way back until the moment when everything was all in one place. That's the moment of creation of the universe. And there are lots of other pieces of evidence. But the simplest one is this. How do you know the Big Bang happened? Go outside at night, it gets dark. If there wasn't a Big Bang, it wouldn't get dark at night, if the universe had been around forever. Beautifully simple explanation. There are subtleties involved, but on the whole, I think that's a very nice way of explaining why the Big Bang happened, that it gets dark at night, and it resolves this centuries-old paradox. Okay, I want to not really say much more. I will say a little bit about time travel paradox, because the paradox of time travel is really the only true paradox in physics, in as much as we haven't got the answer yet. There are no such thing as true paradoxes in our universe. So when we hit one, as I mentioned at the start, that's because there must be something missing in our understanding. Well, it's called the grandfather paradox because traditionally it was about if you were a time traveler and you went back into the past to kill your grandfather before your grandfather met your grandmother, then she would never have given birth to your mother would never have given birth to you, so you would never have been born in the first place. And if you were never born in the first place, who killed your grandfather? It wasn't you. Perfect alibi. Never born in the first place. Couldn't have been you. But if you were never born, then your grandfather never gets killed. Therefore, he does survive and meets your grandmother, and she gives birth to your mother, and your mother gives birth to you. So you are born, so you do go back and kill him. So you're not born, so you don't go back and kill him, and so on. It's a logical paradox like that. This statement is a lie. Now, plenty of time travel stories, everything from Doctor Who to the Terminator, that deal with, and other more recent films, Looper and things like that, that deal with the paradox of time travel. Most of them, if you want to enjoy them, the idea is not to pick holes in them. Like, hang on a minute, how could the Doctor have gone back and met her before she, you're trying to figure it out in your head how it could be logically plausible, and you realise that it's not, because it's paradoxical. You can't, and you just have to enjoy these things for what they are. But I set up the Terminator, a paradox built around the Terminator movie. I guess you've all seen. Has anyone not seen any of the Terminator films? No? Where have you been? Okay, for the benefit of those of you who've not, this is, so let's say something about the original Terminator. The first one was made in the 1980s. Arnold Schwarzenegger, Arnie is the android. He's sent, you know basically the premise, presumably. Yeah. Okay, well, in the future the world is ruled by the machines, the robots, and they want to wipe out all humans. So, but there's the human rebels, the band of humans that are fighting against the machines, led by John Connor. He's the hero. So in the first movie, they send their Terminator, this android, back to the past before John Connor was born to kill his mother, so he'd never be born in the first place. So that's the basic idea. Because it's a Hollywood film, of course, Arnie fails in killing her. Because it's a Hollywood movie, John Connor sends his best friend back to protect his mother, and he does more than protect her. He gets her pregnant, and she gives birth to John Connor. So his best mate is also his dad, and it's all get married. Anyway, it's good fun. But let's force a paradox. What if the machines capture John Connor himself? Don't ask me why they don't kill him, but they send him back into the past to kill his own mother. What happens if he goes and he shoots her dead? Does she, if she dies, does he then just sort of fade out of existence because he was never born? But if he was never born, who killed his mother? You can't rewrite history. You can go back presumably in time and meddle with things, but only to cause them to turn out the way they have turned out. If he's there to kill her, then clearly he must have failed. Otherwise he would never have been born and grown up and gone back to even try. So there's a paradox here. How can he kill his mother? And if he fails, why? It's paradoxes like this that would suggest that time travel into the past is impossible. And yet, and this is what makes it interesting, our best theory of the nature of time is Einstein's general theory of relativity. And in Einstein's general theory of relativity, time travel into the past is at least theoretically possible. It doesn't violate any of the equations of general relativity. So where's the problem? Is there a way of resolving the paradox, or do we have to come up with another theory to replace Einstein's? There are physicists who are seriously studying the notion that time travel into the past might be possible. They don't call it time travel or time machines. That'd be far too dodgy. They would lose respect amongst their colleagues. They call it something like the physics of closed time-like loops or something like that. That makes it more respectable. There are actually two ways out of it. One is that you can travel back into the past, provided whatever you do does not lead to what they call an inconsistent solution. An inconsistent solution would be anything that would cause a paradox. Like John Connor killing his mother. They'll say he can go back into the past, but he will always fail in killing his mother because he must fail because the evidence that he fails is there, that he's there even trying in the first place. He must get born, therefore he must fail. But they don't explain why. Does the hypnotic serum that the machines have given John Connor wear off when he sees his mother and realizes what a terrible thing he's going to do? Does the trigger on the gun get stuck when he tries to shoot her? Is he just a really lousy shot, and every time he aims at her she sort of does a backflip out of the way until he runs out of bullets? They would say that it doesn't matter. It's not very satisfying because it suggests that somehow he has no free will, that the future is now preordained and set like the past. There is another way out of this paradox though, but we don't know for sure if it's the correct explanation. And it is this, and what it calls upon is an idea that many might argue is even more outrageous than the notion of time travel. And that is that our universe is not the only one. That our universe is one of many parallel universes. Like pages in a book, we are the words stuck on one page, but there are many other pages that are always kept separate from us. But if you were to travel back in time, you would unavoidably slide into one of these parallel universes. In the same way that our future ahead of us is open. You could choose to do this, 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 or this. There are lots of options. Similarly, there are lots of paths from the past to reach this present moment. All those paths refer to parallel realities. We've come along a particular path, but if you travel back in time, it's almost certain, because there's an infinite number of them, that you will jump into a parallel universe in which everything could be the same as this universe, apart from the fact that you can go back and change things. So John Connor, when sent back into the past to kill his mother, would slide into a parallel universe in which he can kill his mother. He would just then never be born in that universe, but his own mother, the mother of the murderer, carries on living healthily in his original universe. So as soon as we subscribe to, this is called the multiverse theory, as soon as we say, yep, there are parallel universes, suddenly time travel paradoxes disappear. The problem is we have no evidence that there are parallel universes. It would be nice if there were, because it solves a number of different problems in modern physics, to do with the meaning of quantum mechanics, to do with how come all the laws of physics and the values of the fundamental constants in our universe seem to be exactly right, tuned to allow for stars and galaxies and planets and people to evolve, and for us to ask the question, how come we're so special? That's something called the anthropic principle. Okay, so we'd like parallel universes to exist, but we've got no evidence for it. So until we do, time travel remains the one true paradox in physics that we still don't have the answer to. There are lots of other puzzles and mysteries, but we sort of know, we have an idea of how we might get to the bottom of it. Okay, and so that, I'm not going to talk about the Fermi paradox. Enrico Fermi is one of the great physicists of the 20th century, and he asked a simple question, where are all the aliens? You know, if the universe is infinite, surely someone by now would have contacted us, and if time travel is possible, or someone solves the problem of time travel and builds a time machine in the future, where are all the time travelers? Is another way of putting it. And it leads to, again, this idea of whether there are parallel universes or not, but I didn't want to go into that. Okay. All the stuff is for those, this is my sales pitch, for those of you who do want to know more, it's all in this book where I've collected them all together. I want to stop there because I want to give you a chance to ask me questions. So hopefully we've got about 10 minutes or so, something like that, for questions. So please do stick your hands up. Yes?
That one you said at the start.
Good, thank you. Yes, well done for remembering. Do you know what? Every talk, when I've given this talk, someone always says that, but there was one talk when no one asked, and I said, are you not forgetting something? Yes, so the resolution of the missing dollar. It's a falsidical paradox, which means it's the way I told it. I said, they each pay $9, that's 3 9s are 27, plus the 2 in his pocket makes 29. Where's that missing one that makes up to 30? Yeah, what I should have said correctly was, they've each paid $9, 3 9s are 27, take away the 2 in his pocket, leaving 25, which is what's in the till. There's no longer any $30 you have to account for. It's only $25 you have to account for. They pay 27, 25 in the till, 2 in his pocket. Okay? It's the way I said it. I said, plus the 2 in his pocket. I said it very quickly, so you think, oh, yeah, fine, yeah, 29. So very sneaky, isn't it? You have to subtract, not add. And that resolves it away. And now you can sleep easy at night. Okay, any more questions? Yes?
The alien question, idea of that.
Yeah.
Surely the probability of aliens existing, and that, like, for example, a civilization may exist like 50,000
Yeah, well, yes. I mean, it could be that, so we're saying it's intelligent civilized, that the universe has been around long enough, billions of years, for there to be many other places where the conditions for life would have been right for some other alien life form to evolve, to be sentient, to become civilized, to build spaceships, but then they would have destroyed themselves or become extinct or whatever. Yeah, absolutely, that's possible. In fact, I mean, the resolution of where are all the aliens is a simple one, because you could simply say, well, there should be in principle, especially now that we know, that people like Enrico Fermi didn't know, most stars have planets. And so there must be billions of planets out there that have the right conditions with the right elements, where let's assume carbon-based life forms, the right conditions, atmosphere or even some other form of life that doesn't require oxygen, for instance, spread throughout the whole universe. But the resolution is that the universe is big, and we're constrained by the speed of light. Starship Enterprise, dilithium crystals notwithstanding. And the writers of Star Trek have had to sort of get their act together in the light of physicists saying it's not possible to go faster than light, and they start to, oh yes, but we can crumple up space in front and stretch it out behind us and all. But the fact is, the universe is so vast that the chances of an alien civilization finding us, noticing that there's something interesting on Earth, is so remote that of course the universe seems empty. It might be full of life. In fact, in all probability, there has to be life elsewhere. Why should this planet be so special that it's the only place in the universe where the conditions were right for life? There must be life elsewhere, but there's a good chance we will never encounter it. Not even a signal, let alone a flying saucer. Yes?
So, with the parallel universe's solution to the time travel paradox, well, surely, seeing as we're effectively travelling through time at a second per second, just normally, why is it that it's only when you travel backwards in time that you would encounter a parallel universe?
The theory that suggests that parallel universes will resolve the problem is built on the idea of, in order to travel back in time, you have to hook up two different times. And to hook up two different times, you have to also hook up two different spaces. So you'd need some sort of a space-time wormhole. And a wormhole could link up this here and now part of our universe to somewhere in the past in our universe, but it could also hook up to the past of a parallel universe. So the idea is that all the different realities are all like sheets on a page, and a wormhole is simply a shortcut from one sheet to another. And the notion that if you hook it up, I'm talking, we're hooking up space-times, but that you'd hook it up and that the other end would hook up to your own past is overwhelmingly unlikely given all the number of other parts. If you're going to go to that effort of hooking up space-times, chances are you'll hook it up to another universe. And by the way, that's the reason why people say, where are all the time travelers? If time travel is possible, how come we haven't been visited by time travelers in the future who have figured out how to build a time machine? Well, you can only travel back as far as the moment the time machine is switched on. And so you can't really hook to the past. What you can do is hook it in the here and now and something in the future. And so you can use a wormhole as a time machine to only go back to the moment it was connected up in the first place. But this is all speculation. I'm not talking, this is not part of the proper physics curriculum, because it's all, we don't know. And so we're pushing general relativity to its extreme. Yeah. Right, okay, I'll ask.
Killed the man that invented space travel. But and then when you kill him, and you go back in time, would it still be there to invent space travel?
If you go forward in time.
What
Well,
happened then?
if you go, there's never such a problem if you go forward in time. If someone invents time travel today, and then next week I go forward in time and kill him, the moment when he invented time travel is in the past of the events in which I killed him, so that's fine. So I think going forward in time is never as problematic as travelling back in time, other than the fact that if I could go forward in a week's time, then someone from next week could come back to this moment. Someone from next week could come back to 2 weeks ago and kill the time traveller before he's invented the time machine. There's your paradox. How could they have travelled back in time if they've killed the person in their past who invented it in the first place? Yes?
We accept the theory that the universe is expanding at an accelerating rate.
Yeah.
And it's getting progressively colder. Would we not say that the entropy, or rather, it's getting more ordered, which is sort of going against the laws of entropy?
No, we're still saying it's getting more disordered. As it's expanding and as it's still moving towards thermal equilibrium. And thermal equilibrium is complete random disorder. You know, the opposite of neatness. The fact that it's expanding and there's more space for things to occupy complicates it somewhat, but we still say we start from a highly ordered point, the Big Bang, and ever since then the universe has it's been rolling down the hill. Yes?
When you talk about travelling in time,
Yeah.
and you take it to a different universe, does that mean there's an infinite amount of universes?
Well, first of all, we don't know how many. I personally, I would argue there's just the one universe. But I'm basing that on just, because I'd like there to be, because we don't have any evidence for it. But if there are an infinite number of universes, then parallel universes, then yes, as near as damn it, an infinite number, because every possibility should exist. Now, physicists and mathematicians argue about is it true infinity or just 10 to the 100 to the Googleplex or whatever. As near as damn it, yeah, every possibility should exist. Yes?
If you only believe in one universe, then how do you solve the kind of time travel paradox?
Well, in a simple way, time travel to the past is impossible. And Einstein's general theory of relativity has a loophole in it that we need to close. Because Einstein's theory does allow for time travel, but that may be because of something we haven't understood about relativity theory that would rule it out, and presumably that would await a unification of general relativity with quantum mechanics, so a theory of everything. So that's a simple way around it. But yeah, in my view, if you buy into time travel to the past, you have to buy into parallel universes, and there's no evidence for that. So it becomes speculation, like no different to fairies in the bottom of my garden, which sort of takes it out of proper science and into metaphysics. Yes? Oh, go on then. Whichever.
Can it not be that time travel can only be possible to a time after that time travel has been invented? So let's just imagine it as sort of two ends of a wormhole.
Yeah.
In order for one to come out the other end, that end must first be created.
Correct.
Must have been.
No, yeah, absolutely. If time travel is possible into the past, then that's why when Stephen Hawking says time travel to the past is chronology protection postulate or whatever it is he called it in his 250th time, he says, time travel to the past is impossible, otherwise where are the time travelers? Well, a simple explanation. Time travel hasn't been invented yet. So until it is, then you'll start seeing time travelers coming back in time to that moment, which is still in our future. Yes?
If you could use, theoretically speaking, if you could use wormholes to switch from one dimension to the other, you could do that without switching the time frame, so you could still be in the present while switching universes. Technically, could you be in the same place without having moved?
No. Once you start talking about wormholes connecting different realities, each universe has its own space-time. So it has its own time stream, it has its own space. And so you might not think you've moved, but you are actually in that part of space of the parallel universe. You might not identical to ours, but you have moved because you're no longer in the same reality, therefore you're in a different space. So, yeah. Yes?
If you say parallel universes and time travel exist, and if you move back into time into a parallel universe, well, then how you couldn't get back into your own, would it be kind of like every time, even if you try to go to the future, you're still going to a different parallel universe?
Yeah, I've thought about this. I mean, I think that's if it's overwhelmingly likely that when you travel back into the past, you slide into another universe, then presumably it's going to be overwhelmingly likely when you try to get back, you'll not get back to your own universe. So it's sort of a one-way trip. You'll never return back to your own particular reality. But then parallel universes could be very similar. So you could get back to one that's almost the same as yours. How would you know the difference? It could be identical to yours, apart from someone that you've never met before in China who had 2 slices of toast for breakfast rather than 1. That's the only difference between those 2 universes. So what do you mean by your own universe or parallel one becomes rather obscure. It's great fodder for novelists. You should read, there's a book by Stephen Fry called, I think, Making History, in which he talks about a physicist travels back in time to poison the well in the village where Adolf Hitler's parents live. Well, not poison it, but it makes his father infertile, so they never conceived Adolf Hitler, so Hitler was never born. And in that parallel universe, Nazism still rises up in Germany, and it turns out the Germans actually win the Second World War, so things are even worse. Every reality is possible. It's great for science fiction and novels, but it's not really still the realm of proper physics. Right, I should, I guess, end it here because, apologies, I do have a train to catch.
Thank you very much.
Okay, thank you very much.